This conference will now be recorded.
So, hello students. Now I am explaining the MATLAB program for Butterworth designing Butterworth low pass, high pass, band pass, and band stop filters. Butterworth filter is an IR filter. The main difference between Butterworth and Chebyshev filter is Butterworth filter has monotonic pass band and stop band, whereas Chebyshev filter will have some ripples in pass band and monotonic behavior in stop band. Right now, let us I will share you a screen now, and then explain the low pass filter program, Butterworth low pass filter program. So, coming to this program. So the first is RP is equal to input of enter the pass band ripple, RS is equal to input of enter the stop band ripple, omega p is equal to input of enter the pass band frequency, omega is equal to enter the stop band frequency, Fs is equal to input of enter the sampling frequency. These are the five input parameters that you need to give. Omega 1 is equal to 2 times omega p by Fs, omega 2 is equal to 2 times omega slash Fs. These are called as normalized pass band and stop band frequencies respectively. Why you are normalizing it? You are normalizing it because you have to give in the range of 0 to 1. That's why you are normalizing this particular. The ranges must be from defined from 0 to 1. That's why you are normalizing this particular thing. Next, you are using a command known as n comma omega n is equal to butad of omega 1 comma omega 2 comma rp comma rs. So this butad is a built-in function in MATLAB which is going to return the order and cutoff frequency of the Butterworth filter. So taking into account omega 1 comma omega 2 rp and rs, it is going to return n and omega n. N is called as the cutoff frequency of the Butterworth filter. Omega n is called as the cutoff frequency. N is called as the order. N is called as the order of the Butterworth filter. Omega n is called as the cutoff frequency. And b comma a is equal to butter of n comma omega n. So B comma actually IR filter is a recursive filter which has both numerator quotients as well as denominator quotients. So H of z will be in the form of B naught plus B1 z power minus 1 plus B2 z power minus 2 plus and so on, divided by 1 plus A1 plus J1 z power minus 1 plus A2 z power minus 2 plus and so on. So it will have both numerator quotients as well as denominator quotients. B stands for numerator quotients, A stands for denominator quotients. So taking into account n and omega n values, it is going to return the Butterworth Butterworth low pass filter quotients. B comma is equal to n comma omega n, it returns the Butterworth filter. Omega is equal to omega is in the range 0 is to 0.01 is to 5. So omega is defined from 0 is to 0.01 is to 5. So omega varies in steps of 0.01. The initial value is 0, the final value is 5. H comma OM is equal to next command is H comma OM is equal to freq z of B comma A comma omega. So when you use this particular command, freq z command is going to plot the frequency response in Z domain. Freq z command is going to plot the frequency response in Z domain. So these omega values are plotted in the variable OM and B comma A values they are plotted in the variable H, whatever. So H is a complex frequency response. Actually, theoretically, it's called as h of e to the power j omega, defined as h of n into e to the power of minus j omega n. Actually, it's a DTFT, you can call it. So, when you take the frequency response, when the transfer function is the form of 1 plus z power minus 1, 1 plus b naught plus b1 z power minus 1 plus b2 z power minus 2, divided by 1 plus a1 z power minus 1 plus and so on. If you insert z is equal to r into e to the power j omega, r because r is equal to 1, if you substitute z is equal to e to the power j omega, then the entire this one will be in the form of e to the power j omega. Then once again taking cos omega plus j e power j omega is cos omega minus j e power minus j omega is cos omega minus j omega taking into account, and then bringing in the form of a plus jb, and then theoretically you will be doing like this. Already you know how to plot the frequency response, taking omega values from 0 to pi. etc., and then you will be plotting the frequency response at each and every point, because h will get so many values there, because omega is defined from 0 is to 0.01 is to pi. It is defined from 0 to pi in steps of 0.01. So for each, and there will be totally of 314 values that are there. There are totally of 314 values that are there. For every this 314 values, for every value you will get the a plus jb representation. So it which will have the magnitude as well as the phase. So magnitude will be in the form of root of a square plus b square. Phase will be in the form of tan inverse of b by a. So magnitude is in the form of this root of a square plus b square. This series will be in the form of phi is equal to root tan inverse of b by a. Okay, so like the thing. So after that, uh, this m is equal to 20. You are calculating the magnitude of that. M is equal to 20 log 10 of ABS of H. So you are telling the dB value. Actually, why you are going for dB? Because the gain is very large. If this value is very large, then you go for dB scale, such that you need to minimize that logarithmic scale. Okay, right. So m is equal to 20 log 10 of ABS of H. ABS of H returns the root of a square plus b square, whereas 20 log 10, it is a gain in dB. You are going to calculate the gain in dB. Then, after calculating that particular magnitude and gain, you are going to calculate the angle command. You use the angle command and calculate the phase angle for every a plus jb representation. So, angle of which you are going to calculate that phase, then subplot of 211. So, why you are introducing subplot of 211? Because subplot of 211 means 2 rows, 1 column, first position. Subplot of ABC, A rows, B columns, and C number of positions. That's why you are using this subplot of 211. So there are two plots that are to be plotted here. One is the magnitude response, and the second one is the phase response. That's why you are using two plots here. Subplot of 211, plot of OM slash pi comma m. So you are normalizing that particular variable. You are dividing the 2m divided by pi, and you are plotting against this m value. Then y label of gain in dB, x label of normalized frequency. Okay, so here the while plotting the magnitude response, the first position magnitude response is plotted, and the second this one, this x label, this and type this. Then you are using the title of magnitude response. Then subplot of 212, plot of OM slash pi comma AM, then a y label of normalized frequency and the title of phase response. Okay. Like this, you will be using this particular this one. So you'll be plotting total the magnitude response and phase response of this particular Butterworth filter, low pass filters. Okay. So this is about the logic of this particular program for this Butterworth filters. The main important commands in this that you have to remember are butter, and frequency, ABS, angle, etc. Butter returns the order and cutoff frequency. Butter returns the filter coefficients. Frequency is the frequency response in the domain. ABS of H is the magnitude function. Angle is the phase function. Subplot, of course. The difference between the subplot and figure commands is in subplot you will be plotting the entire this one in this all the figures in the same window. Now I will show you how to execute the program. So you have to type the program now. Now I will show you how to execute this program, how to run this program. I will share you one more screen and then show you how to execute the program. So this is the MATLAB command window. So now what you need to do is you need to run this program. You need to run this program and then enter the input in the command window. I have shared you the command window on the screen. So first you will ask enter the passband ripple. You just enter this 0.5 and the next 45 1500, 2500, next 9000 or 8000. Right. So separately, when you run this, when you this one separately in a figure window, you will get the output. Now I will share the figure window output for you. This is the figure window. This is the figure window that you have got here, showing the magnitude response and the phase response. So this is the magnitude response of the low pass filter. So x-axis you have the normalized frequency 0, 0.1, 0.3, 0.4, etc. 0.5 to 1. Next, you'll have this particular on the y-axis you have 0, minus 100, minus 200, minus 300, etc. So the plot of normalized frequency versus gain in dB is the magnitude response. The plot of normalized frequency versus phase in radians is called as the phase response. Generally, the phase response of IR filters is non-linear in nature. The phase response of IR filters is non-linear in nature. Okay, so this is about the execution of this particular program for the Butterworth low pass filter. Similar procedure is followed for Butterworth high pass filter also. I will show you the program. The entire program is same, especially that there is a minor difference is there. Now I will show you the editor screen once again. Entire program is same, especially that some minor change is there in this particular phase one. So this is a Butterworth high pass filter program. So in this same, there is no switch on, especially one line is different in this particular thing. RP, RS, omega P, omega S, and FS. Omega 1 is equal to 2 times to FS plus omega P, omega S. All the commands are same. Only this command is different. P comma A is equal to butter of n comma omega n comma high. Only this command is different. So in the place of low pass filter, we have used butter of n comma omega n. This is the only command change is butter of n comma omega n comma high. That is it. Remaining things are same. Whatever logic I explained you, the remaining things are same. Okay. Here also this m is equal to 20 log a base of h, n is equal to angle of h. Subplot of 211. In this position, magnitude response is plotted. Subplot of 212, the phase response is plotted. Right. Now let us run this program and give the inputs for this particular thing. The same inputs are entered in this particular this one. The same inputs will be entered for this 0.5, 50, 1500, 2500 and 9000. The same inputs are entered for this. The plot will be different. Run this program and enter the same inputs. Right. I will share the figure window now. So this is a figure window for this particular Butterworth the high pass filter. So you can see that the high pass filter is functioning for the high frequency components. This is for high frequency components, and for low frequency components is that the curve is decreasing, whereas for high frequency components after some higher frequency it is gradually remaining constant. Remaining things is the phase response. Phase response is non-linear in nature, as usual you have, right? So this is about the Butterworth high pass filter program. Next, let us come for Butterworth band pass filter. The same program will work out for Butterworth band pass filter also. So this is a Butterworth band pass filter program. For the same input parameters, you need to give RP, RS, omega P, omega S, and Fs. Omega 1, omega 2, normalized passband and stopband frequencies. Here, N and omega n is different. That's all. N is equal to beta of omega 1, omega 2, RP, RS. Omega n is equal to, you are defining a band here from omega 1, omega 2. Omega n is defined from omega 1 to omega 2. Okay? And that is saved in this inside that particular omega n. And b comma is equal to butter of n comma omega n comma band pass. Okay, that is a command for designing the band pass Butterworth band pass filter coefficients. Butter of n comma omega n comma band pass. Okay, omega is equal to 0 is to 0.01 is to pi. Once again, omega is varied from 0 to pi. H comma om is equal to freak of b comma a comma omega. All these things are same. Angle is of h, subplot of 211, subplot of 212. All these things are same. Okay. Now let us same input parameters are there. So you are going to give the same input parameters for that. Let us run this program. So this is the enter the in same inputs in the command window, and the figure window is generated here. I will show you the figure window now. This is a figure window for the band pass filter. It is going to pass a set of bands defined from 0.3 to some 0.4. So whatever the cutoff frequency omega 1, omega 2 is joining a band and it is passing the particular bands. The remaining things are just zeros. So normalized frequencies versus gain in dB, normalized frequency versus phase in radians. So this is a figure window for the band pass filter. So the last type of last filter is band stop Butterworth band stop filter. So this is the program for the band stop filter. Entire program is same. Only one command is different. As I told you, n is equal to buttout of omega 1, omega 2, RPRS, omega is equal to omega 1, comma omega 2, and b comma a is equal to butter of n comma omega 1, comma stop. These are the uh, this is this is the Butterworth band stop filter. So it is going to stop certain set of bands and remaining the allowing the remaining bands of frequencies. Right. Now I'll enter the inputs, run the program now. So this is a figure window for this particular band stop filter after entering the inputs. So the x-axis is normalized frequency, y-axis is gain in dB. So first one is plot is the magnitude response, second plot is the phase response. So it is going to stop certain set of bands and allowing the remaining bands of frequencies. Okay. Okay, right. So this is about the procedure for designing the Butterworth low pass, high pass, band pass, and band stop. Thank you.